We have seen queue implementation with arrays. Queue implementation with arrays has limitation. Suppose if we have array like this, rare reached maximum index and front is at index 2. Here queue is not full. If we try to insert one more item, it will raise error queue is full. Since linear queue overflow condition is if rare equal to max minus 1. If this condition satisfied, then queue is full. Here this max is the array size. If we turn this array into closed circle, we can overcome this situation. Means we can insert even rare reach to the maximum index if we have space. If n is the size of the array, then computing indices modulo n will turn the array into circle. In circular queue, this last position is connected to this first position like this circle. Here I am taking an array named as Q. Here I am taking the array of size 8. You already know rare is used to keep track of most recently added item and front is used to keep track of least recently used item. When Q is empty, both front and rear will be at minus 1. Suppose we want to add first element into Q, that should be added at the 0th index. So we need to set this both front and rear to 0. If array is empty, in that situation, front and rear will be at minus 1. So we need to set both front and rear to 0. Now add this element to the queue at the rear index 0. Now our queue will have one element 5. Here this is the logical representation of the array as circular queue. Suppose we want to add another element to queue. Now here queue is not empty, means we have one element within our queue. So for this second enqueue operation, rare will be incremented. So previously rare was at 0, now rare will be 1. Now add this element 6 at the rare index 1. If we perform one more enqueue operation, these are the queue contents after these 3 enqueue operations. Now rare is at index 2. Suppose if we perform these 8 enqueue operations like this, then rare would be at index 7. Suppose if we want to perform one more enqueue operation, but see here queue is full. If we increment rare, then rare would be 8. There is no index with 8 within our queue. If we try to access the index 8 in our array, we will get error. To avoid that condition, we will write this if condition. If rare equal to max minus 1 and front equal to 0, we should not perform the enqueue operation. We should raise error queue is full. Observe here, while implementing linear queue, our overflow condition is only if rare equal to max minus 1. But here, for this circular queue, front also should be at index 0. If front is not at 0, suppose if it is at 2, these two locations are empty. Then we can utilize that space. So in circular queue, overflow condition should be like this. Suppose two elements are removed from queue, then front would be at index 2. Means we have free space. In linear queue, we cannot utilize this free space, whereas in this circular queue, by changing this rare increment statement to this statement, here modulo increment is used. Here rare is index 7, rare plus 1, it would be 8, 8 modulo array size, here array size is 8, 8 mod 8 would be 0. Now rare would be 0. So we can add elements at this 0th index. Suppose two elements are inserted, 3 and 4. For the next enqueue operation, we should get queue overflow error since queue is already full. So this queue overflow condition will not work because front is not at 0. Here front is at index 2 and rear is at index 1. So change this overflow condition like this. We inserted two elements, so rear is at 1 and front is at index 2. Rear plus 1 means 2. 2 mod array size, it is 8. So result is 2, which is equal to front. Front is also 2. So we can raise the error queue is full. So let's modify this overflow condition. Now updated Overflow condition would be this one. Now this will work for all cases. Assume we have queue like this. Front is at index 0 and rear is at index 7. If we want to remove an element from the queue, we need to perform DQ. If queue is not empty, then DQ should return least recently added item. Here one is the most recently added item, so least recently added item will be 5, means this DQ should return element which is at index front. Then we need to increment this front because front should point least recently added item in the queue. So add this statement, then return the element at the previous front. Now front is at index 1, previous front means 0. We already stored that element at index 0 in the variable x, that x will be returned here. If we want to remove one more item from queue, same process will be repeated. After removing this 6 from the queue, now front will be at index 2. For this 7th DQ operation, it will return element 8 and front will be at index 7 and rear is also at index 7. If we perform one more DQ operation, Q will be empty. So this front and rear should be set to -1. This kind of situation will occur when front and rear are at same index. So let's add this condition for our procedure. If front equal to rear, front and rear will be set to -1. Here we perform one more DQ operation. So front and rear set to -1. Let's consider another case. Suppose if we perform 3 NQ operations on Q like this. Here front and rear are at same index. After performing these 3 NQ operations, now rear would be at index 2. If Q is like this, in this case we want to perform one more DQ operation. Here front and rear are not equal, so this increment for the front condition will not work for this circular queue, because if we increment this front it would be 8, but there is no index 8 in our circular queue. We need to change like this: front equal to front plus 1 modulo array size. If we have this increment condition for front, if we DQ one item, then this front 7 plus 1 which is 8, 8 mod 8, result is 0. So now front will be at index 0. On this queue, if we perform 3 more DQ operations, queue will be empty. If we try to perform one more DQ operation on this empty queue, if queue is empty, front will be -1. On empty queue, we should not perform DQ operation, so we should raise error. Means if front is -1, we have to raise Q is underflow error. So add this condition to our DQ procedure. This is the complete program for circular queue implementation with array. Here we took the array of size 8. Initially front and rear are initialized with -1, means Q is empty. This is NQ function. It has one parameter. NQ checks for overflow condition. If Q is not full, NQ increments the rear index when Q is not empty. If Q is empty, front and rear will be set to 0 and adds this element E to the Q at the rear index. This function is not returning anything, so its return type is void. This is DQ function. It will check for underflow condition. If Q is not empty, it returns element at front. Then we need to increment the front if Q has more than one element. If Q has only one element, means front will be equal to rear, then front and rear will be set to -1 because Q will be empty after deleting this element. This display function will print the contents of the queue. We need to check whether Q is empty or not. If Q is not empty, print the contents of the queue. This for loop will print the elements before rear index. This print statement will print the last element, means element at rear. If we execute this program, Here we are performing 3 NQ operations, the elements 5, 6 and 7. So these are the contents of the queue, 5, 6 and 7. And here we are performing one DQ operation. It will remove the element at front. 5 is at front, so 5 will be removed from queue. Then we are adding this 8. So stock contents are 6, 7 and 8.